And we're back. Welcome back and happy Tuesday. Today, we will pivot to generalization theory. We will develop a general framework expanding upon the idea of growth functions that makes a combinatorial argument to further abstract the notion of complexity of the hypothesis set in a very elegant way. All right, so before when we met, we talked about the idea of a growth function, and this growth function counted the largest number of dichotomies that a hypothesis set was able to induce over an in-sample set of n many data points. And the growth function satisfies this upper bound of 2 to the n possible dichotomies because we assign one of two choices, plus 1, minus 1, to each one of these n many data points. Now, we talked about the growth function for three increasingly complex hypothesis sets: the positive rays, the positive intervals, and the convex sets. And we saw that for each, the breakpoint changed from k equals 2 to 3, and lastly, for the convex set, it had no breakpoint, so we said the breakpoint k is infinite. And so we said if no breakpoint exists, the growth function is precisely equal to 2 to the n. And if any breakpoint exists, we said the growth function is polynomial in the data set size. So today we're going to move along a construction and associated proof to actually show that the growth function is in fact polynomial. And so we argued that our growth function is polynomial in n, and we'll do this by proving a bound on the size of that growth function. And so to show that the growth function is polynomial, we'll show that the growth function is less than something that is itself less than or at most polynomial. And so the key quantity we're going to discuss, we'll introduce some new terminology, a function bnk, and this bnk is going to be the maximum number of dichotomies. So dichotomy, to jar your memory, is an assignment of plus 1, minus 1 labels to each of your big N many sample points, in sample points. And we're going to assume this bnk counts the maximum number of dichotomies on n many data points with a breakpoint of k. And so we're going to do this purely by combinatorial argument over the data set size. And the reason why we do this is because it's free of any reference to a notion of a hypothesis set, as well as any reference to the input space or feature space. And because, and this last part is particularly important, because it's combinatorial, we can actually come up with an exact expression for this quantity, which is very important. And so with this, we'll make a construction, and this is going to give us the ability to form this bound on bnk, the maximum number of dichotomies on a data set of size n with a breakpoint of k. We're going to put a bound on that and then show that the bound itself is polynomial. And so here we construct a table. And in this table, along the columns, we're going to depict, let me set my pen. Along the columns, we're going to depict each of our in-sample points. So we have x1, x2, all the way up to including xn. And so this is going to be our data across the columns. And then the rows are going to represent all of the unique dichotomies, these patterns of plus 1, minus 1, are labels on our data points. And so here we have n columns, and we're going to have some number of dichotomies, so each row is a dichotomy, that you can induce on a data set of size big N. Now, of course, we said that the breakpoint is going to be k. And so as we described before, a breakpoint is defined as the size of the data set, k, where you can no longer generate all possible 2 to the k many dichotomies. And so we're going to list out our dichotomies, And then we're going to arrange this table in a particular way. And so this first section up top, that section is going to correspond to the unique dichotomies. And what I mean by that is that this first section is going to comprise all of those dichotomies that are unique in their pattern +1, -1. And so here, this +1, -1 uniqueness is going to be with respect to the first n-1 inputs. And so for the first n-1 positions for all of the dichotomies in this first section in the table, each one of these +1, -1 dichotomies, these labels for n-1 many inputs, are going to be unique. So there will be no repeating patterns. Now, of course, if these repeating patterns are unique for the first n-1 positions, this last position, it doesn't matter if it's a +1 or a -1, these dichotomies will still be unique because they're unique in the first n-1 places. The next two rows or sections are going to be a little bit different. Now, for these next two sections, we're going to arrange them based on the first n-1 positions, but for every entry in this first region here, and this first region is called S2 plus, the patterns are going to be the same one-to-one with those patterns for the first n-1 positions for the dichotomies in the second region here that we call S2 minus. Now, where these two patterns differ for S2 plus and subset S2 minus is going to be in that nth position. And so for the S2 plus dichotomies in that set, it's going to have an nth position that's going to be a +1. And for the S2 minus, they're going to have an nth position for their dichotomy that is a -1. But everywhere else, for the first through the n-1th position, all of the dichotomies in set S2 plus and S2 minus are going to be the same. And so we have the first group that are unique dichotomies, unique patterns of +1, -1 in the first n-1 positions. And then we have S2 plus and S2 minus that are not unique. And so this dichotomy is the same as this dichotomy for the first n-1 places. And then for that last place is where they differ. This copy has a +1, and that copy in S2 minus has a -1 as that extension, that last position, that nth position. And so when we describe these sets, we have set S1 is a set of unique dichotomies in n-1 positions, and S2 plus and S2 minus are the non-unique dichotomies in the first n-1 positions. Okay, so now with that, we're going to put some measurements here to count the number of dichotomies for each one of these subgroups. We have alpha as the number of rows, and therefore the number of dichotomies that have unique patterns for the first n-1 positions. And then we have size beta to represent the number of rows or dichotomies in set S2 plus. And now because you have a copy of each row in the first n-1 positions in set S2 plus in set S2 minus, if S2 plus has a size of beta, the number of rows in set S2 plus, so too will set S2 minus. It will also have beta many rows for beta many dichotomies. Okay, so we list all of these out, and with this grouping together, we can count all of the dichotomies on a data set of size n given a breakpoint of k. So we just add these up. That's alpha, that's set S1, plus beta, that's set S2 plus beta, that's set S2 minus, for a total bnk is equal to alpha plus 2 beta. And so these are all of the patterns of 1 and 0, the dichotomies, for our data set of size n given a breakpoint of k. All right. So now, given this construction, let's direct our attention to this region, first region, and the second region. And so what we're going to do is count the number of dichotomies for this subregion, and we do this to set up our recursive expression for what the bound is on BNK, the unrestricted version. And so here, we're going to remove that nth column and look at the unique dichotomies that we get for this augmented version. Now, if we look at our columns, well, our data set is no longer of size n. Our data set is of size n minus 1. And of course, because we've limited or lessened the number of dichotomies because we don't include this second set, S2 minus, because when we remove that nth column, we now have two copies of the dichotomies in S2 plus. Because again, from our construction, we arranged them such that S2 minus and S2 plus had the same dichotomies from the perspective of the first n minus 1 in sample points, our data set. And so again, when we count our dichotomies, we're counting unique assignments of +1, -1 labels to our data set. And so we have to remove this other section. We're not considering that section. And so if we were to count these dichotomies and put an expression for the number of dichotomies, the maximum number of dichotomies given our breakpoint, well, we reduce the data set and we know for sure that the breakpoint has not changed because we reduce the size of this table depicting our set of dichotomies. But what we did do is strike from consideration this nth data point. And if we strike that from consideration, then this is going to change to be the bound or the maximum number of the dichotomies we can get on now a data set of size n minus 1 given that same breakpoint k. Now, if we count these, well, by the scheme, we have our first group was of size alpha. That was our set of unique dichotomies in n minus 1 positions. And our second group here of size beta will also be added to that count for b of n minus 1 and k. And so here we have the count is alpha plus beta, and that alpha plus beta is bounded from above by this bn minus 1k. And so here we're focusing solely on the first n minus 1 data point, and now we're looking at the number of dichotomies we can get given n minus 1 data points instead of the full n data points that we had before when we had this closed expression equals for bnk. All right, so we have that alpha plus beta is at most b n minus 1 and k. So now let's turn our attention just to this section, that section of that we call the non-unique dichotomies. And these, again, to jar your memory, it was the set of dichotomies that are not unique in the first n minus 1 digits. Now, of course, when we focus on these rows, we said before, for every element that we have in S2 plus, we also have an S2 minus. And so S2 was just the union of these two, and these were the non-unique dichotomies in n minus 1 digits. And so if we were to look at these counts, well, this number of dichotomies, if we think about what's happening here, we have two copies. We have one copy in the S2 plus, and we have another copy in the S2 minus. And so we have some number of dichotomies. And we said that these dichotomies, the S2 plus and the S2 minus sets, that the only difference was that nth digit, that nth position. And so one copy for this can be extended by making that nth position a +1, and the other can be extended by making that nth position a -1. Now, if we had a breakpoint for this first subset, S2 plus, if that breakpoint were k, well, what would happen here? Well, we could extend this by having another copy with the nth position as +1 and the nth position as -1 for each one of these respective rows in S2 plus, and that would double the size and the count of the number of dichotomies. And so if that's the case, that means that we cannot count this set S2 plus as having a breakpoint of k, because this represents half of this portion that we alluded to in the earlier slide when we included in our count S2 plus and S2 minus. And so when we refer to just this S2 plus region, one of those non-unique dichotomies, here we're focusing on a subset of the rows, and we refer to this beta is just going to be the count, the upper bound of the number of dichotomies on a data set of size n minus 1, still n minus 1 because we only include the patterns on the first n minus 1 position in the table, and the breakpoint is now k minus 1 because this represents a halving of the total number S2 that we had from before. And so this breakpoint is k minus 1 because this last row column adds +1 and -1 extension, this +1 and -1 on two different copies, and it represents a doubling, and so it can't be k. It has to be k minus 1 because it represents a halving of the number of dichotomies. All right, so now we take our original expression for our bound, b and k, the maximum number of dichotomies given a data set of size n and a breakpoint of k. We said that was alpha plus 2 beta. And we take our expression for the two subsets that we had, and that was the non-unique set of dichotomies and one of the unique set of dichotomies. And we counted that as alpha plus beta is at most b n minus 1k. And then we took one of the non-unique subsets of the dichotomies, and we said that's bounded by above by the maximum number of dichotomies on a data set of n minus 1 with a breakpoint of k minus 1. And so now substituting in for this b and k, well, that alpha plus 2 beta is the same as saying alpha plus beta plus beta. So now if we substitute for this first alpha plus beta, this upper bound b of n minus 1 comma k, and we substitute for this beta, this upper bound of b of n minus 1 k minus 1, we get the following expression that b and k is less than equal to, or at most, b n minus 1 and k plus b of n minus 1 and k minus 1. So this step is just substitution. And so this gives us a recurrence relation that expresses the maximum number of dichotomies on a data set of size n with a breakpoint of k in terms of smaller subsets. The max number of dichotomies for a data set of size n minus 1 with a breakpoint of k, and the max number for a data set n minus 1 with a breakpoint of k minus 1. Okay, so we reduce the data set size, and then we additionally reduce, for that reduced data set size, we reduce the breakpoint. So we put those two together, and that's going to give us our full max count of dichotomies for a data set of size n with a breakpoint of k. All right, and so if we look at this expression, we can think about what these values are for arbitrary n and k. And this is getting towards the proof of the fact that this b and k is polynomial. It represents the upper bound, but it's also polynomial. But we'll start out by considering what this recurrence relation, how it unfolds for different instantiations, all the instantiations of n and k. So in order to prove that this b and k is polynomial, we start out with the boundary value conditions. And so here in this table, we have k along the columns, and that's the breakpoint, and we have n along the rows. That's the data set size. So starting out, we consider what happens if we have a breakpoint of 1, so a data set of size 1, and where you can no longer generate all possible 2 to the 1 dichotomies, and the data set is of size 1. Well, that's a vacuous argument, but nonetheless, it means that if you have a data set of size 1, how many ways can you assign a label? 2, plus 1 or minus 1. And for whatever reason, the hypothesis set for this scenario cannot generate both the plus and the minus label, and so we have a dichotomy count of 1. And so if we go along this row, going to the right, let's look at the case where the breakpoint is 2. So if the breakpoint is 2, that means that we cannot generate all possible 2 to the 2 data dichotomies. And so 2 to the 2 is 4, but for a data set of size 1, we can generate all 2 to the 1. So we have a dichotomy count here of 2. Likewise, if the breakpoint is 3, but the data set size is 1, well, we only have one data point. So once you reach 3 data points, it can no longer generate all possible dichotomies. Okay, well, 2 to the 3 is 8, so the max is 7, but you can't have 7 because you only have one data point. So we write a 2, because you can assign plus 1 or minus 1 labels to that single data point 2 different ways. And then we also, for the same reason, write 2 and 2 and 2. And so that's the base case for, or the boundary value condition for having a data set of size 1, regardless of what the breakpoint is. So let's take a look at a breakpoint of size 1, regardless of what the data set size is. And so here, if we can no longer produce all 2 to the 1 dichotomies, or 2 dichotomies, we can only produce 1, either a plus label only or minus 1 label only, regardless of how big the data set size is. So of course we have 1, 1, 1, 1, going all the way down. Now if we look at this recursion, well, the bn minus 1k, well, if we look at the position of n, for a particular value of n and k, if we go up in the rows, that's n minus 1, and if we stay in the same column, that's k. So if this particular value is bn comma k, if we go up in our table, well, that's reducing n by 1, so that would be bn minus 1 comma k. And if we go up and to the right, well, or to the left means that we're reducing k, the breakpoint, by 1. So that would be bn minus 1 going up, and then k minus 1 going once to the left. And so this would represent bn minus 1 comma k minus 1. And so if we look at this, these blue points, those are the expression, the addition of them are the expression for the right-hand side of this bound on b and k. And here, this clear point here, that is b and k. And so we can use this scheme to fill in the rest of the table. For example, if we have this value and this value, the first one, that's going to be our bn minus 1k minus 1. Here, we're going to have our bn minus 1k, and so we're going to add the 2, and that's going to be 3. And so we can use this recurrence relation to fill in all the entries of our table describing the max number of dichotomies, b and k. All right, so if we do this, we see this table populated, and you'll notice here, after a point, we get to a maximum value in each row. So we go 1 to 2, and then all 2s, 1 to 3 to 4, and then all 4s. If we look at this entry, well, we have a breakpoint of size 3, so that means it can't generate all 2 to the 3 or all 8 dichotomies, but we have 2 data points, and so we can assign 4 different ways +1, -1 labels to these two data points. So we have a total number of 4 dichotomies. But once you get past k equals 4, it remains 4 because you have 2 data points. In similar fashion here, if we look at k equals 3, our breakpoint is 3, that means we can't generate all 2 to the 3 dichotomies, or 8 dichotomies. So we have 3 data points. Well, that means we stop short of 8, which is 7. And that 7 is exactly this 3 plus this 4. And so we can fill in all the entries of the table, but now we need a more sophisticated way that talks arbitrarily about the entries in this table, describing the bound on B and K, the max number of dichotomies that you can have for a data set of size n given a breakpoint of k. And so an analytic solution will allow us to get to that point where we can prove that the upper bound on B and K is in fact polynomial. And recall, we needed to prove that it's polynomial because a negative decaying exponential can overwhelm the dampening factor of a polynomial to make sure that the right-hand side of the union bound on Herfting's inequality will result in a very small probability, which is what we're after, to have a small probability that in-sample error and out-of-sample error would diverge. And so here we have our closed form expression, and we're going to prove this by going through our base case, proved by induction, and then show for the inductive case that this does hold true. So here we have B and K, and N here is the same N. K represents the upper bound on the index of summation. And so the index of summation is K minus 1, where the parameter value for B and K is K. And so we have B and K is at most the sum for I goes from 0 to K minus 1 of N choose I. All right. So let's take this approach, and this works for any hypothesis with a breakpoint of K. And that's the beauty of the analytic solution. So now we're going based on a combinatorial, pure combinatorial argument from the data set, which is divorced from the hypothesis set itself, even though the hypothesis set has a breakpoint associated with it. And this will result in an expression that will tell us whether the descriptiveness of that hypothesis is polynomial and therefore amenable to good performance out of sample, meaning Herfting's inequality for the union bound is very, very small probability associated with that bad event where in-sample error diverges from out-of-sample error. And so we're going to start with the boundary value conditions. And for these boundary value conditions, we're going to plug in n equals 1 and k equals 1 and demonstrate that this is in fact the case. And so for n equals 1 and k equals 1, we have b of 1, comma 1 is at most the sum I goes from 0 to k minus 1, so that's to 0, of n choose I. Well, of 1 choose I. So that's just 1, that's our n, choose 0. So 1 choose 0, well, there's just one way to do that. That's equal to 1. And yep, lo and behold, absolutely, that is 1. Okay. And so if we were to show that same expression, b of n equals 1, there's our n, and k equals 2, there's our k, that would be bounded from above. I goes from 0 to 1 of 1 choose I. So that would have two terms. That would be 1 choose 0 plus 1 choose 1. Okay. And so 1 choose 0 is 1. So there's a 1. And 1 choose 1, well, that's just 1 factorial over 1 minus over 0 factorial, which is 1, over 1 factorial, that's 1. That's just 2. So it'll be 1 plus 1 is equal to 2. And here we have it, 2. And so we can show that this is, in fact, the case, this bound, for all of the base case values. And we can plug in n1 n equals 1 and k equals 1, we can choose any of these, this first row or this first column from our table and plug into this expression for the bound on b and k and actually show that it is, in fact, true. Okay, so that being the case, for proof by induction of this expression being the bound on b and k, the maximum number of dichotomies for a data set of size n given a breakpoint of k, now we go to the inductive step. And so we assume true for the blue cases, and we show for the inductive step, which is this expression right here. So how are we going to do that? Well, we're going to actually show that this sum is true by filling in our definition for the bound on b and k and show that we get back this result. Okay, so let's take a look. So here we have b and k, and that was our original expression. And we said b and k is b of n minus 1k. So this is b of n minus 1 comma k. And this is b of n minus 1 comma k minus 1. Okay. And so let's take a look at this. So if we were to plug this in, we want to show that b and k is equal to this expression. And of course, for b and k, we're plugging in for that definition of b and k as just being the sum, I goes from 1 to k minus 1 of n choose I. I goes from 0 to k minus 1 of n choose I. All right, so let's do this. So here, this is our b and k, and this is our assumption, assuming that it works, and we want to show that we get this b and k. And so we're going to assume bn minus 1k and bn minus 1k minus 1. So here is our n minus 1k. And so k is here, so we write k minus 1. The sum, I goes from 0 to k minus 1 of n minus 1, choose I. Okay, that's our first one. Now our second one, okay, that's the same as saying the sum, I goes from 0 to k minus 1 minus 1, which is k minus 2. That's where we get the k minus 2. n minus 1, choose I. So now we're going to simplify this a little bit. So when we go from this first step to the second step, we examine this first term here, and we examine this second term here. So starting with the first term, we notice that if we were to evaluate the summation on the first term for which I equals 0, n minus 1 choose 0 is always 1. And so we're going to unroll the summation and rewrite this term by taking out the iteration for I equals 0. That leaves the sum for I equals 1 to k minus 1 of n minus 1 choose I. If we evaluate n minus 1 choose 0, that's nothing more than just 1. So there's our 1. And so this 1 plus the summation I goes from 1 to k minus 1 of n minus 1 choose I is just the equivalent of this first term on the right-hand side of equality that you get by peeling off that I equals 0 term. All right. So now for the second expression, we want to get the index of this second expression to start from I equals 1. But nixing us is this I equals 0. So we're basically going to do a dummy variable substitution. And so everywhere we saw I equals 0, we're going to write I equals 1. So if you were replacing I with j and said everywhere you see I equals 0, you see j equals 1, that means when you do the replacement here, that's going to be subtracted by 1. And likewise, if I is equal to k minus 2, that means we're going to have the upper bound change to k minus 1. So we're just changing our dummy variable, effectively incrementing the index I by 1. That's the new version of this variable. but we need to account for that by subtracting 1 inside of this expression. And so the new version of this expression, our equivalent expression, using that dummy variable replacement, is the summation I goes from 1 to k minus 1 of n minus 1 choose I minus 1, because this I is going to change when we do this dummy variable substitution, and this dummy variable just happens to be the same name as it was before. So now that we have this, we make an observation. Now with this observation, we see that these two expressions, n minus 1 choose I, n minus 1 choose I minus 1, they're under the same type of summation with the index going from 1 to k minus 1. So we can combine the two. When we combine the two, we have 1 plus the summation I goes from 1 to k minus 1 of this combined term, which is just n minus 1 choose I plus n minus 1 choose I minus 1. And so with this expression, we can combine them, and we can certainly do this algebraically. And when you look at what this expression means, this expression is the same as saying n choose I. So one way to say n choose I, suppose that you're in a room and you have a group of n people and you want to choose a team. So you could choose that team of some size, that where the team includes me, or if the team excludes me. And so in the case where the team includes me, well, that's just one of the slots in the team is myself, and the other n minus 1, you're going to choose some number. Okay, so here is the case of the team excluding me, because out of those n people, you exclude me, and you're going to choose that team of size I. Here's the case of the team including me. So if the team includes me, well, you're not going to choose I team members. You can choose I minus 1 because I'm going to occupy one of those slots. And of course, you can't use all n because one of them, myself, was already picked to be in the team. So this is the team includes me, and this is the team excludes me. And so if you add these two together, that's the same as choosing a team of I people from a total population of n, where I'm among that population. And so you could also do this algebraically, and you can work out what n choose I, n minus 1 choose I is, n minus 1 choose I minus 1, and do a lot of canceling. But the argument holds. It's absolutely true. And so this expression in the parenthesized or square bracket, n minus 1 choose I plus n minus 1 choose I minus 1, we can replace that with n choose I. And so this gives us the equivalent expression, and write it over here, of 1 plus the summation I goes from 1 to k minus 1 of n choose I. Now, of course, we take a look at this 1, and we note that this 1 is the same as saying n choose 0. So we can write n choose 0 plus the summation I goes from 1 to k minus 1 of n choose I. Now, of course, we can fold this term, n choose 0, which is 1, back into the summation, and that changes the index, and we get this expression, the sum for I goes from 0 to k minus 1 of n choose I, which is exactly what we set out to prove. And so this is the inductive step, and because we've set no restriction on what n and k are, it applies for all n and k, and we've proven that this holds true for all n and k by induction. All right, so this, when we show our growth function is bounded from above by this b and k, which is bounded from above by this summation I goes from 1 to k minus 1 of n choose I, the maximum power in this is polynomial in k. And so if we take a look at this expression, let's take a look at what happens when we have this upper index, right, k minus 1. So if we do that, well, let's look at what n choose k minus 1 might be. So that's, of course, n factorial over n minus k plus 1 factorial times k minus 1 factorial. Okay, so if we take this expression, this n factorial, we can decompose that as n times n minus 1, and then eventually we get dot 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 times n minus k plus 2, and then we get n minus k, subtracting again, plus 1, and then we have all the other terms going down to 2 and 1. Now, of course, if we look at this expression, let me just rewrite this, n minus k plus 1 factorial, k minus 1 factorial. So if we look at this expression, these terms are the same as writing n minus k plus 1 factorial. So this expression then becomes n times n minus 1 dot 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 times n minus k plus 2 times n minus k plus 1 factorial over, we have n minus k plus 1 factorial, we have k minus 1 factorial. And so these two terms will cancel, and we're left with, in the numerator, n times n minus 1 times n minus 2 dot 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 times n minus k plus 2. Now, over k minus 1 factorial. Now, if we look at this expression, and if we were to multiply out the polynomial associated with these terms, n times n minus 1 dot 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 times n minus k plus 2, well, we're multiplying n times n times n times n with itself, k minus 1 many times. Now, of course, if you multiply n by itself, k minus 1 many times, that's going to be some polynomial with the highest degree is n to the k minus 1. And so that just says that this expression is going to be a polynomial at the most whose degree is k minus 1 in n. And so you could absolutely cancel other terms with this k minus 1, but this k minus 1 you can think of a constant because we've already canceled out all of these terms, right? And so these terms here, if n is large, is going to dominate the denominator, and this denominator is going to look, because k, the breakpoint, is fixed, this is going to be a constant, right? So we have some constant, which is that 1 over k minus 1 quantity factorial times n, something that's of the order polynomial of degree n to the k minus 1. So this upper bound on the growth function on a data set for a hypothesis on a data set of size n, given a fixed breakpoint k, we know that this is bounded from above for this reason by something that's polynomial in the data set size n. So it is, in fact, polynomial bound. All right, so let's go back to where we were before, and we're going to revisit the breakpoints and growth functions associated with some simple hypotheses of increasing complexity. We had the positive rates, we have positive intervals, and then we also looked at the line on the plane, namely the 2D perceptron. And so armed with this upper bound on B and K, the maximum number of dichotomies, let's take a look at the positive ray. Now for the positive ray, we said the breakpoint K is equal to 2, and our growth function is n plus 1. And so if we look at the bound, we evaluate this B and K are bound, and if we do this bound, the breakpoint is K equals 2. So if we evaluate B and 2, that's less than equal to our sum, I goes from 0 to 2 minus 1 is 1 of n choose I. So that's equal to n choose 0 plus n choose 1. Okay, so if we do that, n choose 0, that's 1, and n choose 1, that's n. So we get 1 plus n, or n plus 1, and that's exactly what our growth function was for the positive rays. For the positive intervals, we said the breakpoint was k equals 3. So now we take our breakpoint of 2, and that gives us an additional term. So in this particular case, for the positive intervals, we have b of n, comma, 3 is equal to the sum, or less than equal to at most, I goes from 0 to 3 minus 1 is 2, and choose I. Well, we know what n choose 0 and n choose 1 is. That's just n plus 1. So what is left, say n plus 1, what is left is that term for I equals 2, which is n choose 2. All right? So if we have n choose 2, n choose 2 is nothing more. N choose 2 is n factorial over n minus 2 factorial over 2 factorial. Well, that's just n times n minus 1 times n minus 2 factorial over n minus 2 factorial over 2 factorial is 2 times 1, which is 2. Well, n minus 2 factorials cancel, so that's n times n minus 1 over 2, which is n squared minus n over 2, which is just 1/2 n squared minus 1/2 n. Now, of course, we already had n plus 1. So we have n plus 1, and then we're going to add to it that 1/2 n squared minus 1/2 n. So we're going to say n plus 1 plus 1/2 n squared minus 1/2 n. So we have 1/2 n squared. We have n minus 1/2 n, so that's just plus 1/2 n plus 1. So that's 1/2 n squared plus 1/2 n plus 1. And that's exactly the bound on our growth functions, and exactly our growth function that we had calculated before exhaustively. So when we looked at the 2D perceptron, well, we found that the breakpoint k equals 4. So now we have b of n, 4 is going to be the upper bound on the number of dichotomies. Well, we already know from breakpoint of 3, that's just equal to 1/2 n squared plus 1/2 n plus 1. But what we're doing is we're adding to that. We have the sum, I goes from 0 to k minus 1, is 3 of n choose I. And so we now need to add to this expression n choose 3. And n choose 3, let me do the calculation up here. N choose 3 is nothing more than n times n minus 1 times n minus 2 times n minus 3 factorial over n minus 3 factorial, and then 3 times 2 times 1, 3 factorial is 6. And so the n minus 3 factorials cancel. We're left with n times n minus 1 times n minus 2 over 6. We multiply these, so that's n times n squared minus 2n minus 3n plus 2 over 6. That's equal to n cubed minus 3n squared plus 2n, and we have 1/6 under each of them. 1/6, 1/6, 1/6. Okay, and so if we do that, well, that's just, let me write it down here. It's a little bit messy. That's just, we have 1/6 n cubed minus 3n squared over 6. That's just minus 1/2 n squared. And 2 over 6, that's 1/3 plus 1/3 n. And so we're going to add those to the 1/2 n squared. So we have 1/2 n squared plus 1/2 n plus 1 plus what we had for that expression for n choose 3. Okay, so we have 1/2 n squared and minus 1/2 n squared, so the n squareds are going to cancel. And then we have an n cubed that doesn't have anything. We have 1, and then we have 1/2 n plus 1/3 n. And so we're going to write 1/6 n cubed, and then we have a plus 1, and then we're going to put together the 1/2 n and 1/3 n. 1/2 n plus 1/3 n, that's just 3n plus 2n, which is 5n over 6, which is just 5/6 n. So we have 1/6 n cubed plus 5/6 n plus 1. And there's our result for the bound on the number of dichotomies given a data set of size n and a fixed breakpoint of 4 for the 2D perceptron. And if we look at the growth function, this bound, regardless of what it is, which is why this bound is important, is our 1/6 n cubed plus 5/6 n plus 1. And so because it's combinatorial, it gives us the ability to compute an algebraic expression, closed form expression, for the upper bound on the number of dichotomies associated with that breakpoint. And so now we can actually calculate a number that will represent the complexity and therefore the expressiveness of our hypotheses. And this is completely divorced of counting hypotheses, looking at equivalence classes, because it's a combinatorial argument we're making with this treatment based on the data set. Okay, so with that, that's all I had to say, and we will pick up next time. As usual, please stay healthy, stay safe, and I'll see you all on Thursday.